All right, Margaret, I had time to make a short video for you about this. Hopefully you read your textbook and do some problems. Ionization energy and electron affinity are very different in terms of what they're describing and the numbers that you see, although they're in the same chapter because they have something to do with each other. So here's what I mean. So if you look at this slide I made you, the ionization energy is the energy needed to remove an electron. So I have just a generic atom X, and I say, what if I ripped an electron off and made a +1 cation and had that extra electron? That's going to cost me energy. Notice I said it's a positive amount of energy. The delta H for this is called the first ionization energy. Again, it's an element in the gas phase, and it's the energy associated with taking an electron off. This is related to some other periodic properties you've seen that all have to do with the Z effective. Remember how atoms get smaller when you go left to right, and they get bigger when you go down? Well, ionization energy is similar. In other words, ionization energy gets larger and smaller when you go down. Okay, for the most part. There's a couple of exceptions. Read about those in your book. Okay, I'm not going to take time to do it here. But the point is that it's the energy, it's a positive delta H associated with removing one electron from a neutral atom. There is such a thing as the second ionization energy, or the third ionization energy. Notice what it is and what it's not. Here is a generic second ionization energy. You're starting with the +1 cation, and you're yanking an electron off and making a +2. That's also going to be a positive delta H, because it's hard to pull an electron off of an atom. In fact, it should make sense to you that it's harder to pull off the second electron than the first, always. Why does that make sense? Well, if you're taking an electron off something that's already positive, you have to use even extra force. Now there's something interesting here. If this second electron is in the core, it's really hard to pull off. Like normally, if you were just doing a regular atom, pulling off the second one would be about 2 times greater. Now, I'm going to say about. But if you're doing a core electron, it's about 10 times greater. Just think about lithium, for example. 1s2, 2s1. Pulling off the first electron is taking off a valence electron, but pulling off the second electron is pulling off a core electron. That's going to be really hard. In fact, I bet that there's a table in your book showing ionization energy for several atoms. This is a true statement. Whenever you go to a core electron, the ionization energy is always way bigger. Like here's an example. Let's do boron. Boron is 1s2, 2s2, 2p1. So that means that if you take off 3 valence electrons, those are increasingly going to get harder. But if you want to take off the 4th electron, that's a core electron, and so it's way harder. Finally, on this little video, I want to mention electron affinity. This has to do with adding an electron to a neutral atom. So it's not the opposite of ionization energy. It's adding an electron to a neutral gaseous atom. So it's the delta H associated with this. Now, most of these values are negative. Not all of them, most of them. I'm sure there's a table in your book. Usually it's important for students to realize that what the trends are. The trend is that the halogens have the largest negative electron affinities. By the way, my book uses a different term. It's called electron attachment enthalpy. So I don't know what your book does, but my book does that. So hopefully that makes sense, right? If you're a halogen, you love having an extra electron because you want to have the same as a core. Because if you have F-, that's the same electron configuration of neon, and atoms love being noble gases. I hope this helped. Bye.